Okay, hello and welcome everyone. So in this video, I'm going to do a review session for the first exam for Intermediate Micro. And this is going to be over consumer theory, which is the subject matter for exam 1. So I'm going to start off thinking about a variety of preference shapes of different utility functions and how we'd approach those types of utility maximization problem. So the first one, suppose we have perfect complements. This is going to look generally something like this. So utility is coming over our consumption of good X, good Y. It's going to be whichever is the smaller of this alpha coefficient times the amount of X and this beta coefficient times the amount of Y. Remember when we had this preference shape, we could replace this comma with an equal sign, find the line that it's actually going to be a ray through the origin that's going to go through all the corners of these right angle indifference curves. Then when you found that relationship, you'd substitute it into the budget constraint and you'd solve for the optimal X star and Y star. We'll see a numeric example later on. If we have perfect subs, it looks something like this. Utility is coming from good X and good Y, and it's the weighted sum of this alpha times the amount of good X and this beta times the amount of good Y. We're just taking the sum of X and the sum of Y. And what we do here is we would compare the marginal rate of substitution to the price ratio and generate three possible outcomes. You can think of those three pictures where we have relatively steeper indifference curves compared to the budget constraint. That gives us Alex, our all X solution. Suppose we have relatively flat indifference curves relative to the budget constraint. That gives us Ali, or our all Y solution. And then suppose the indifference curves, the marginal rate of substitution, the slope of the indifference curves, the marginal rate of substitution is equal to the slope of the budget constraint. Now we've got our BC solution. This is where the indifference curve is going to be coincident with the budget constraint, and anything along the budget constraint is going to be optimal. There's going to be a whole continuum of solutions. If we had Cobb Douglas preferences, now we're going to use calculus directly. We'll set up our Lagrangian. So suppose we had a preference shape like this. It's going to be X to the alpha, Y to the beta. Ultimately, we'd want to get our tangency condition, which in this case is going to be, with Cobb Douglas, it's always going to be like Y over X times a collection of constants, or times constants that are coming from these exponents. When you get your tangency condition and then set equal to the price ratio, when you get your tangency condition, you're going to substitute into the budget constraint and you find the optimal X and the optimal Y. And we'll see an example of that shortly. And then for quasi-linear preferences, it might look something like this. So you've got some alpha times X plus some beta times log of Y. Here, we're going to try to get the marginal rate of substitution, set it equal to the price ratio. And what ends up happening, what's kind of bizarre about quasi-linear, and this might throw you off initially, is the demand for one of the goods is going to be immediate. It's going to drop out immediately from comparing the MRS to the price ratio. The other one you're going to arrive at by substituting what would be the tangency condition into the budget constraint. Suppose we had this sort of hybrid perfect substitutes and perfect complements preferences. This is where it's like substitutes, but it's embedded in this complement shape. Right? This gives us these, here you have indifference curves where you don't quite have right angles. They've got some slope to them. They still have corners. You can approach like the ordinary perfect complements to relate X and Y, get the ray through the origin that connects all the corners of our indifference curves, and that'll be one possible location for the solution. The problem is now that we've got some slope to the so you'll have some they won't be perfectly right angle. You'll have some slope. Then you have this situation where you have to look at the wings of the indifference curves to compare that to the slope of the budget constraint. There's actually 5 locations where the solution could be. It could be at one axis or the other. It could be at the kink, or it could be along one of those wings, depending if the budget constraint had the same slope as this portion or this portion. And we saw examples like that. Okay, so the other type of problem we saw was the consumer's expenditure minimization problem. Here, and I guess in general, with thinking about utility maximization, you want to keep clear what's the objective function and what's the constraint. So our formula, our format is always going to be either to minimize or to maximize some objective subject to some constraint. That minimization or maximization is by choosing some amount of good X and good Y. In this case, we are going to minimize the expenditure. This is the objective function subject to our constraint. In this case, the constraint is to hit this level of utility, U upper bar, given this preference shape, given these, whatever is this utility function. Right, so with the consumer's expenditure minimization problem, the objective is to minimize the expenditure necessary to hit some utility level. Now, if this is a calculus exercise, you'd find the tangency condition, and then you'd solve it into the constraint. If it's not, you'd begin your reasoning around the goal of hitting this utility level, being able to have enough of each of the two goods at the lowest possible price necessary to hit this level of utility, given whatever is your utility function. That would be our general approach. All right, so now I'm going to do a couple of exercises. Remember, this is at the end. This one right here is from the end of the IMX exercises, and IMX1 exercises, and it's also from the end of, I believe, the income and substitution effects lecture. So, but I want to go over this again because this is a nice sort of perfect complements problem. I can embed it in this interesting development. So the first thing is we've got this utility function. We want to find the demands given the following prices here and this income level. Then suppose the price of good 1 falls. Now we want to find the demands again. Then in part C, we're saying, all right, well, let's find the level of income at these new prices that would have been required to consume the bundle that we got at the old prices. And that's what we're doing in part C. Then in part D, you're saying, okay, well, let's find the optimal bundle at these new prices. Price of both goods is 1, when the consumer would have whatever was that requisite income we found in C. And then we're going to use this to compute the substitution effect and the income effect. Remember, the substitution effect is the change in consumption due to the price when purchasing power is held constant, and the income effect is the change in consumption due to purchasing power changes when price is held constant. Okay, and then we comment on the findings. So the first part, well, this is just solving a standard perfect complements problem. And so I'm going to replace this comma with an equal sign, solve for x2. That'll give me the equation of the line through the origin that connects my corners of my indifference curves. So that's going to be the line x2 is equal to 1/3 x1. That's this right here. I'm going to substitute that into my budget constraint. My budget constraint is going to be 3x1 plus 1x2 is equal to 40. That's this right here. Now I've made that substitution. I've replaced x2 and then just solving. You'll notice how I did this. I wanted to get a common denominator. You wouldn't have to, I mean, rather than working with decimals because that's horrendous, I'm just going to say, oh, wait a second, I've got a 1/3 here. I can write 3 as 9/3. Now I've got 10/3. That multiplies through really nicely, and this breaks out to 12 units of good 1. Well, if I'm consuming 12 units of good 1, then how much good 2 am I going to have? 1/3 times 12 is 4. That's this right here. All right, so that's my original bundle. This is right here, my original bundle. Now the prices have changed. So for part B, the price of good 1 has fallen to 1, right? Previously it was 3, now it's 1. Here's my new budget constraint, x1 plus x2 is equal to 40. My right through the origin, my preferences haven't changed. So this relationship is still the same. I'm going to drop this into my budget constraint, now substituting for x2, and I'm going to use my same trick as before, getting a common denominator. Rather than 1 right here, I can write that as 3/3. That gives me 4/3 x1 is equal to 40. And then I find I want 30 units of good 1, 10 units of good 2, right? And so this is my new bundle. Now in part C, I want to find the income that would be required to consume the original bundle, 12 and 4, at these new prices. So when the price of good 1 is 1, price of good 2 is 1, and I consume 12 units of good 1, 4 units of good 2, this costs me 16 units of income. So this is the income, 16, that's required to consume the original bundle at the new prices. Now let's find the optimal bundle at the new prices when the consumer actually has 16 units of income. So suppose I have 16 units of income and these are the prices. What's the bundle I'm going to get? Through all this, all what's changing is the budget constraint. So now my budget constraint, my preferences still have the same shape. And so this relationship between x1 and x2 at the corners of my indifference curves is still going to be the same. So I'm going to drop this relationship into my budget constraint, which is going to be constructed from using these prices. Price of good 1 is 1, price of good 2 is 2, and this income, which is 12. So this right here, I kind of regret having written step D like this. I omitted one important step, which is like I should write out 1 times x1 plus 1 times x2 is equal to 16, right? That is the budget constraint I'm using here. I've made this substitution. Obviously, I've just replaced x2 here immediately, but if you're just kind of staring at this work, that might be difficult to follow. Anyway, now going through, I find, indeed, at these new prices, when the price of both goods is 1 and I have 16 units of income, I want 12 units of good 1, 4 units of good 2. Okay, well, that should be the case based on how we've constructed this. But anyway, now what I want to do is I want to use the values I found to get the numerical values for the substitution and income effect. So I'm actually going to scroll down. I'll just show you this solution for a second, and then I'm going to go to where I wrote it up probably a little bit nicer. All right, so I don't need to take a screenshot or whatever is the case, but I got it here as well. So, all right, again, we had part A. These were the prices. Price of good 1 is 1, price of good 2 is 2, 40 units of income available. Here was the bundle I wanted. Now in part B, the prices of each good were 1, my income was still 40. Here's the bundle I got. Then in part C, we were looking at, technically, so part C we were finding the income that was required to get the original bundle. That's where we found it was 16 above. And then part D is where we're actually doing the comparison. So let me go up to where we were actually working on part E, so let me be careful about that. So for part E, we wanted to find the substitution effect. Find the substitution effect, find the income effect. Okay, so the substitution effect is just how much the consumer changes consumption of good 1 in response to change in price while holding purchasing power constant, right? So the purchasing power had to go from 40 to 16 after the price change to retain the same purchasing power. So for the comparison here, we are comparing how much we were buying of good 1 in part A and part D. Oh, part A was right here. Good 1 was 12. Part D was, right here, also 12. So my comment, this should be unsurprising that this matches part A since we built it from the income found in C, which was precisely what was necessary to consume the bundle A after the price change. Now for the income effect, here we're interested in the change in purchasing power given the change from M to M hat while holding prices constant. This is the change in consumption given by, 30 to 12 is 18. That was from comparing part B to part D. Right, in part B, we had the new prices, but the original income. In part D, we had the new prices, but the analogous income to prior to the price change. And we found, my amount of good 1 ended up going from 12 to 30, right? And so the income effect here is the change in prices was 18. This is prices held constant, comparing 1 and 1, 1 and 1, but the income changed, and my consumption of good 1 changed from 12 to 30, so 18. This is the income effect, and then my comment was the entire consumption response comes through the income effect. This happens because there's no substitution at all. These preferences are represented by perfect complements. That's unsurprising given the preference shape, right? These are perfect complements preferences, and there's no scope for substitution with perfect complements. All right, so the next thing I want to do is I want to look at perfect subs. So here, look at this utility function. My utility over good x and good y is coming from 50 times the amount of good x plus 150 times the amount of good y. Suppose I have 600 units of income. Price of good 1 is 10, price of good x is 10, price of good y is 30. Find x star and y star. Find the optimal bundle. Well, my marginal utility of x, take the derivative with respect to x, is 50. My marginal utility of y, take the derivative with respect to y, that's 150. 50 divided by 150 is my marginal rate of substitution, that's 1/3. What about my price ratio? Oh, that's going to be 10 divided by 30, which is also 1/3. My marginal rate of substitution and my price ratio have the same slope, which tells us one of my indifference curves is going to be coincident with the budget constraint. And this tells me that as long as I'm on my budget constraint, I'm optimizing. And there's actually infinitely many bundles that would work. So that's my comment. We get a continuum of solutions. And here is my budget constraint, right? The maximal amount of y I could get, 600 divided by 30 was 20. Maximal amount of x I could get, 600 divided by 10 is 60. The slope of the budget constraint was minus 1/3. Slope of the indifference curve is minus 1/3. Or if you want to talk in absolute value, slope was 1/3. See, I did 1/3, 1/3. Why? Well, we know those are going to cancel when we compare anyway. And so very often, similar to the comment from Varian, economists are just going to talk in absolute value when it comes to marginal rate of substitution and price ratio. Okay, so now I want to look in greater depth in terms of this example. So the top part is just exactly what we did before. Same utility function, same prices and income. Find the optimal, okay. Here I'm comparing marginal rate of substitution to price ratio. And look how I built this out. The marginal rate of substitution is MUX divided by MUY. Price ratio is PX over PY. We can do some clever cross multiplying just with the variables here. And I can write rather than MUX over MUY and PX over PY, I can write this as MUX over PX and MUY over PY. And look what's happened in between. Of course, it's preserved the relationship, right? So these are just two alternative ways of doing this analysis. You could do literally the MRS compared to the price ratio, or you could do what we'll call our bang for your buck rule, which is comparing marginal utility of X to the price of good X, marginal utility of Y to the price of good Y. And we can use both to build our intuition here. I like the second one for what I'm going to do next, which is answer the question of what do we do if the price of good X falls? Well, if the price of good X falls, we're going to get a greater than sign here, right? Price of good X falls, we're going to get a smaller number here, which means with a smaller number, you'll get in the denominator, you get a larger fraction. This would tip us toward the all X solution. All X is when MUX over PX is bigger than MUY over PY. What if the price of good Y falls instead? Now that'll make a smaller denominator here, so a larger fraction. So that would give us the less than sign. This would tip us towards the alley solution, right? So if the price of good X fall, if we're currently at the situation where we're on our budget constraint, like we're currently in this situation, and good X becomes cheaper, what's going to happen? We're going to buy only good X. Or what if we're in this situation and good Y becomes cheaper? What are we going to do? We're going to buy only good Y. All right, so that's what all this is to say. It's help us think about how these changes could affect our consumption bundle. Now here's a Cobb Douglas. Suppose our utility is going to be X to the 1/3, Y to the 2/3. The price of good X is 2, price of good Y is 3. The income is 60. Here's my Lagrangian. I'm going to maximize utility. So my objective is my utility function. My constraint is my budget constraint. Here's my lambda. I'm going to take dL dx, which is my marginal utility, is going to give me marginal utility of X. And then here's dL dy, which is going to give me my marginal utility of Y. dL d lambda is just the budget constraint. All right, so where did this come from? Well, take this derivative. It'll be take this power out front, 1/3 X to the minus 1 or minus 2/3, because you have to reduce the power by 1. And then this Y to the 2/3 comes along for the ride. This is going to be a minus 2 lambda from this right here. And then down here, I'm going to have 2/3 X to the 1/3. This X to the 1/3 comes along for the ride. Reduce this power by 1 brings me minus 1/3. And then looking at this, wait a second, I can divide this one by this one, because right here is like literally my marginal rate of substitution. Right here is literally my price ratio. Price ratio is going to be 2/3. Marginal rate of substitution is going to be, well, I can write this out. Suppose we'd actually solve for lambda, but my marginal rate of substitution is going to be this right here. Suppose we hadn't done it this way. Suppose we had solved this for lambda and then substituted. That would give us this. This is familiar. This is our bang for your buck condition, right? This is literally the marginal utility of X divided by the price of good X, literally the marginal utility of Y divided by the price of good Y. Set these equal, and then solving, this gives us our tangency condition. And my comment here is that this is not a demand. This is something that gets substituted into the budget constraint. This is the tangency condition after I clean this up. This is not my demand for good Y, nor is it my demand for good X. We're not done. The demands are of the form PX, PY, and income. All right, so now I'm going to plug into the budget constraint, and when I do this, I can evaluate, I can find my optimal amount of good X and my optimal amount of good Y, right? So this is going to be 2X plus 3Y. Here I've substituted my tangency condition into my budget constraint, and then solving, I get 10 units of good X, and then solving over here, I get 40 over 30 units of good Y. My generic Cobb Douglas demands, if you remember them, would be alpha over alpha plus beta, m over px for my Marshallian demand for good X. Y star, my Marshallian demand for good Y, is going to be beta over alpha plus beta, m over py. So this boils down to 1/3, because that was my alpha, right? Alpha plus beta is 1 in this particular problem. And then this is just beta, 2/3, because alpha plus beta, again, was 1. And then my income was 60. Income is 60. And then the price of good X was 2, price of good Y was 3, and sure enough, this matches. Could you do this? Well, yeah, as a check step. For a longer question on the exam, I'd actually want to see your work here. If you're just doing a multiple choice question, very well, you might want to go ahead and just kind of skim to the front by doing the generic Cobb Douglas demands, assuming you've got the right functional form. All right. Suppose we have quasi-linear utilities, so this is going to be utilities coming from good X and good Y is going to be 2X, this is the linear portion, plus 3 natural log of Y. Suppose the price of good X is 4, price of good Y is 3, my income available is 18. My marginal utility of X, that's just the partial with respect to X, that's 2. My marginal utility of Y, that's the partial with respect to good Y. Well, the derivative of the natural log of Y is 1 over Y, so it'll be 3 over Y. My marginal rate of substitution then is going to be, well, this divided by that, which gives me 2y over 3. I'm going to compare that to my price ratio, which is 4/3. And then this gives me, well, my demand immediately for good Y, right? It drops out. You're like, wait a second, I got to do something else. No, with quasi-linear utility, remember, one of them drops out immediately. Here it's going to be my demand for good Y. I'll plug this into my budget constraint, and then solving, I get my demand for good X, right? Because I have to exhaust my budget. The last thing is I want to say, look, this consumer really wants 2 units of good Y. Will actually not consume beyond 2 units of good Y. Once reaching 2 units of Y, this consumer starts buying good X. Well, what if the price, so how does this compare to the income? What's the income necessary to buy 2 units of good Y? Well, the price of good Y was 3, so you need at least 6 units of income to be able to buy those 2 units of good Y. And it turns out if we want to look at the demand relationship, if my income is bigger than 6, the consumer still gets Y stars 2, but I have to exhaust my budget. So if my income's less than 6, what do? Well, I can afford less than 2 units of good Y. So here's one thing I want to reflect on is look at my margin rate of substitution relative to the price ratio in this situation. So if my income is less than 6 and I've got less than 2 units of good Y, then this 2, here's my margin rate of substitution, 2Y over 3 is going to be something smaller than 4/3 because this right here, this numerator is going to be something smaller than 4 because Y is less than 2. But if that's the case, this is in the direction of all Y, right? The margin rate of substitution is less than the price ratio. That's in our direction of our alley solution. This isn't perfect substitutes. This is quasi-linear. However, we can borrow this intuition that when the marginal rate of substitution is smaller than the price ratio, you want to shift your consumption towards Y. And this is what it's telling us, is that our consumer, if their income rises, is going to boost their consumption of Y at least until this becomes equal. And that's going to happen here. Here you can compare my marginal utility of X to the price of X, marginal utility of Y to the price of Y, and then see, sure enough, this happens exactly when we have less than 2 units of good Y. Okay, and then my comment here, expenditure minimization review. Well, I've got some videos on expenditure minimization, so you'll have a look at that. There wasn't an example there. Anyway, I sure hope you enjoy the exam review video, and I'll see you next time.